Hello, and welcome back to the course on distributed systems and security. In this video, I would like to briefly talk a bit about cryptocurrencies and smart contracts. So what we did in the previous videos was talking about state machine replication. And cryptocurrencies is a special case of this, and so is smart contracts. And it's basically the application where you take something like a bank with programmable accounts, and then you replicate it over many services instead of running it inside one bank. That's one way to think about it. So to make a cryptocurrency, and a well-known example is the Bitcoin cryptocurrency. What you do is you start by giving your new currency a name like Bitcoin. And then you create a replicated state machine, which is keeping track of who has how much of this currency. So it's just, you can think of it as just a big map, let's call it account, which is mapping account names, let's for now just pretend that it's the name of the account owner, into how much is on the account. And so to begin with, typically, I mean, there are some initial accounts that will hold some of these coins, and the rest of them will be distributed typically to the ones that's helping to run the replicated state machine. This could, for example, be that if the replicated state machine is running on top of a totally ordered broadcast channel, like the one we saw in the previous lectures, then you would give some of these coins here to everyone that helps produce a block. Who could just, I mean, if it goes round robin, who will make a block, then to incentivize the servers to actually be running, you would give them a little bit of a Bitcoin every time they make a new block. That's one typical way to pay for running these systems here. Okay. Anyway, so the idea is you have this totally other broadcast channel, and that you use to implement a replicated state machine. And the only thing that this replicated state machine does is to keep track of this state here, which is called account, and how the money are moving around. So what you can do to this replicated state machine is to give it an input which makes money move from one account to another one. So for example, if you give it an input which triggers a payment from the account called Jesper to the account called Ivan, the only thing the state machine will do is decrement by 7 the account of Jesper and increment by 7 the account of Ivan. That is clearly a state machine, right? It only changes state according to inputs, and it has some state here, namely the accounts. So we can take this thing, and with the machinery we have from the previous videos, we can create a distributed system where this account here is replicated over, let's say, 1,000 different machines that are all running it. And even if, let's say, 333 of these machines are trying to kind of steal the money by moving them around, they can't, because we could assume that, let's say, strictly more than 2/3 of these machines are honestly running the system and therefore honestly maintaining these accounts. So that looks like a pretty weird way to implement a bank. We can return later a little bit to why you would do that. Anyway, let's look at a few simple crypto problems if we wanted to do a cryptocurrency like this. The first thing is, if anyone could tell this replicated state machine to move money, there would be obvious ways to steal money. I mean, it could have been that it was even telling the system to move money from my account to his account. And that I wouldn't like that. Another big problem is, how do these, something like Bitcoin, how does it attain value? I mean, how would these numbers end up being worth money? And that's maybe the most magical thing. The way it happens is that if you're lucky and you create your cryptocurrency, something like Bitcoin, and it so happens that at some point people start being willing to exchange real world objects for corresponding transfers of these things on the chain, well, then it becomes worth something, right? So let's say somehow if I transfer 7 of these cryptocurrencies here to Ivan, he would be willing to give me a banana, right? Then somehow, I mean, we get an expectation of, oh, it looks like if I transfer people Bitcoin, they're willing to give me real world stuff in return. And then a cryptocurrency could attain value. And this is what happened with Bitcoin, for example. The first known purchase of a real world object using Bitcoins was done in May 2010, as far as I remember. Someone bought a pizza for 10,000 Bitcoins. And then because people thought, haha, that's funny, you can buy pizza for Bitcoin. I mean, they started to have an expectation that, I mean, maybe you could buy all other stuff for them. And then from there, it became a speculation object. So people were like, ooh, so if these are worth money now and they weren't yesterday, maybe the price will keep going up. So people started buying Bitcoins. And then because there's a limited number of Bitcoins and there was speculation, the price skyrocketed. And by today, those 10,000 Bitcoins that were used to buy a pizza is worth, as I think, something like 114 million US dollars. So we must hope it was a very good pizza, because that's certainly a steep price. Okay, so that's the magic part of it. That has nothing to do with distributed systems. But I mean, if you create like a planet-wide peer-to-peer system that's keeping a track of who have how many Bitcoins, apparently it can happen that these Bitcoins become worth a lot of money. That's step one. Another problem is, of course, Ivan shouldn't be able to tell the system to transfer Bitcoins from my system to from my account to his account. So instead of naming the accounts kind of with who owns the account or something like that, instead the account names are the public keys of signature schemes. So basically, for each possible verification key for the signature scheme used, there is an account. Now, to spend money from an account, you need to know the corresponding signing key. Okay? So the way you make an account in the system now is basically just you generate a public key, signing key pair for a signature scheme. And now you're now the owner of the account with that verification key. And since you generated the key pair, you also know the signing key. So if there would ever be money on that account, you can now move them away, but only you can do it, because if you want to transfer money away from a given account named by a verification key, it's required that it gets signed by the corresponding signing key. Okay. So for example, here, I mean, to send money from one account with verification key VK to another one with verification key VK prime, let's say 7 of the cryptocurrencies, you would have to send along a valid signature. So it should be true that if you verify under the verification key of the sender, then, and the message is 7 and then VK prime, which would mean I would like to transfer 7 to account VK prime, then the signature here should result, it should be valid. And of course, the account that you're transferring from should contain at least 7. And if this is true, we decrement the sending account and we increment the receiving account. Okay. You might have a worry that, wait, if the verification key is the account name, couldn't someone just steal my account by generating a key pair with the same verification key and thereby know the secret key? And the answer is, of course not, because if the signature scheme had this property, then anyone could also forge signatures. If they wanted to sign under some verification key that's not their own, they could just generate a key pair with that verification key, know the signing key, and then sign on behalf of that verification key. And as we saw in earlier lectures, we can design signature schemes that are actually secure. So we know that in particular, you can't just choose to learn the secret key of some target account. So that is in fact a secure way to establish an account. You just generate a key pair, and now you own the account that is named by the verification key. Then, of course, you would need someone to transfer your money, but you could tell the place where you work to transfer money to this account in the future, because you would like to get your salary in Bitcoin. And then you're off the ground, you have your own Bitcoins, and you can transfer them around in the system. Okay. Then we talk a little bit about how to replicate this thing. So the way the Bitcoin system originally was imagined was that you would replicate it using a totally ordered broadcast channel, but not really of the form that we have looked on in the previous sections, where we imagined like something like maybe 7 servers, out of which we could tolerate 2 being corrupted. Instead, it was imagined that you have a totally ordered broadcast channel somehow implemented on top of a planet-wide peer-to-peer system, a system where anyone can join. So maybe there's millions of servers. And if you want to use the system, maybe you are adding your own server to the system to help run it. And then again, the system is built, as a matter of fact, such that it can tolerate that up to 49% of the servers are corrupted. So it's imagined that you build a planet-wide peer-to-peer system with 1 million servers that will then honestly keep track of the holdings on these accounts as long as, that's annoying, 499,999 of these servers are not colluding to break the system. And if these servers are distributed across the planet from enough companies, maybe thousands of companies taking part in running the system, millions of users, all from different countries, it's probably a fair bet that not half of them will get together to break the system. In particular, because the people running the system would typically also be the ones that have money vested in the system. Okay? So that's kind of the crazy vision. And it's quite important that whatever you build there, whatever is keeping track of these accounts, is actually a totally ordered broadcast channel, like the ones we looked at in the previous videos. It's easy to illustrate with an example why this is. So let's imagine that we have an account with 100, let's say, Bitcoins here. And then simultaneously, let's say 2 different places on the planet, it issues 2 transfers. One where it transfers 60 to that account, and one where it transfers 60 to that account. These transfers will propagate in the peer-to-peer system. Some of them will see this transfer first, and some other people will see this transfer first. And it's clear now, if I try to transfer 120 away from this account here, the last transfer needs to be rejected, because we can't have accounts going in minus. That just counts as creating money out of the blue. I might be transferring to my own accounts here. So we really need to reject the last one such that the account never goes in minus. But remember, it's a replicated system. There's 1 million servers on the planet, all keeping track of what are the balance on these accounts. And we are resting our security on the fact that they keep the same account, they keep the same ledger, as it's called. But then it's also very important that they agree which of these 2 transfers were the last one, because it's the last one that needs to be rejected. We cannot have half of the planet rejecting this transfer, and then this keeping 12, and the other half rejecting this transfer and bringing this account here into 72, because then the system is now inconsistent, and it breaks the consistency of the system. Now, if we go back and look at some of the systems we looked at in the previous lectures, it's clear that these will not be practical, totally ordered broadcast channels if there's 1 million servers. In particular, I mean, the number of messages just in these systems will kind of n squared at least. So everyone speaks to everyone in each round. And 1 million squared messages, that's a lot of messages. And you just drown the internet in each round just to produce a block in such a totally ordered broadcast channel. But there's a different problem, how you would implement that. And it's in fact a problem that we will return to in the next series of videos, when we are looking at what is called Nakamoto style consensus, or also how to build Bitcoin and modern totally ordered broadcast channels for planet-wide application. But let's ignore that for now. Let's just assume that we could do that. We have an efficient, replicated, planet-wide kind of replication of an account system. The cool thing with that is that if these Bitcoins, or whatever we would call the given cryptocurrency, there's a lot of them around now, we would have a planet-wide kind of money system where anyone can transfer to anyone, and this money attain value. And yet we're not resting this system onto any central bank or any country, or even any government. So you would have a system that anyone could trust, and where we wouldn't have to transact between people, actually agree on which currency to use and which regime to trust. That's kind of the vision behind doing these things. Okay. Such a system can be made much cooler by the use of blockchains. Oh, this was the slide where I should have been speaking about the blockchains. So this word blockchains, just to put it in context, remember what we said on the previous slide is that it's important for cryptocurrency, which is just a replicated list of numbers, that is run on top of a totally ordered broadcast channel. Now, if you recall the previous videos, when we implemented a totally ordered broadcast channel, we had this notion of sending out blocks. So someone would just take some incoming outstanding commands, put them in a block, and then announce it. And then someone would announce the next block, and someone would announce the next block. So that's just creating a sequence or chain of blocks. That's all there is to it. So the word blockchain is just saying you're creating the sequence of blocks, which are then containing these transactions. And then we have some underlying mechanism to make sure that we all agree what is that sequence or what is that chain. Okay. So it means we will sometimes use this when we're talking cryptocurrencies. We'll interchangeably say blockchain and totally ordered broadcast, but it's really just the same thing. The blockchain is just the underlying totally ordered broadcast mechanism. As I said, the vision would be to create one where anyone could add a server, and therefore you will get so massive replication that no organization or country could attack the system and break it down, because they can't take over half of the system. Okay. But as I said, it can be made much cooler. So the next level up that some cryptocurrencies are doing is they say you can have this notion of a smart contract. This really just means you can associate a little bit of code to a smart contract, to an account. And then this piece of code here, it will kind of auto-execute. It's like a tiny virtual machine. In fact, it's a tiny state machine associated with the contract. And it has power to act on behalf of the account. So it can actually make payments on behalf of the account. And then it can be programmed to react to certain events, and thereby being a contract. So we could maybe I could put a contract here, which would say, if some football match tomorrow ends up with team A winning, I will transfer 7 Bitcoins to that account. Yeah. Then that would be a way to like algorithmically implement gambling, which would most likely be illegal, but it was also just an example, so don't go home and do that. It could also be that it pays money in case that there's proof that some event for an insurance policy was fulfilled, or in response to the US dollar to euro price reaching a certain level, and then it would pay because someone did a future on that. You can imagine many ways to program it. The important thing is that since this piece of program here is allowed to act on behalf of this account, in particular, move money out of it, again, not anyone should be able to put this piece of code here on the account, only the account owner. And the way that is done then is that when you want to associate a smart contract to an account, you sign the smart contract with the signing key of that account. Remember that the account, again, is just named by the verification key of a signature scheme. So if you want to do something on behalf of the account, you always sign with the corresponding signing key. So that means now to kind of create a smart contract, it really means you write a smart contract. It's just a piece of code. Let's call it M for machine. It could be in Java, it could be in Haskell, or it could be in any programming language that the blockchain supports. Then you send a message on the blockchain that you would like to associate or create this smart contract on that account. You send it on a signature. And again, if under the name of the account, the verification key associated with the account, or being the name of the account, that the signature is true on that thing, then all the servers in this replicated system will take M and associate it with the smart contract. And then it can't be removed or overwritten. It sits there forever, and that's what makes it a contract. And then what happens is that this contract can be triggered by certain events that makes it do something. Remember that it's a state machine, so it doesn't do anything on its own. It's not that it's sitting there and computing, but it can react on certain messages on the totally ordered broadcast, for example. And those can come from various places. And I'll just look at a few examples now. So one way that a smart contract could be triggered is that it gets an external input from the owner of the account. So that would just be, the way that would be done is that the owner of the account would like to give an input to its smart contract. So it would sign X again with the corresponding signing key. So we know it comes from the owner of the smart contract. And then just put this thing onto the totally ordered broadcast. So remember that underlying the account system, we had this totally ordered broadcast. And we can also use that to signal to all these smart contracts. If you send something there, then it will appear in some well-defined order, all these events or inputs to the system. And then all the servers in the system will run all the smart contracts on this sequence of messages that appear on the totally ordered broadcast channel on the blockchain. And then the smart contracts can be designed to do something on some particular inputs. Of course, most of these inputs are for other smart contracts and they will just ignore them. But for example, an external input could come and that message signed by the owner of the smart contract. So the smart contract knows, oh, this is an input to me from the owner, so I better act on it. And then based on this X here, it will do something. One thing that it could do is send signals to other smart contracts. And typically, the only way actually to get to send an input to a smart contract that's not your own is to use an external input to trigger your own smart contract, and then that one do the transfer. The way that this works then is this smart contract, let's say it got an external input. It saw this, it's been looking at the sequence of messages appearing on the totally ordered broadcast channel, blockchain, I should call it blockchain. And then this external input came. This is a state machine. So it says, oh, this is an input for me. I will change my state and then I will produce an output. And then if the output is of the form send X prime to account VK prime, then we will take that. I should have had an X prime here. Then we take that as meaning that this smart contract has decided to send an input X prime to this smart contract. And that might then in turn trigger that smart contract to send some other input to some other smart contract. So you can have a whole ecosystem of smart contracts implementing, let's say, some kind of financial service. So this here could have been me triggering some app to transfer you money, and then they end up on your app, like when in Denmark one is using mobile pay. So you could imagine a mobile pay that is not running on top of a banking system, but on top of a planet-wide cryptocurrency with these techniques here. In that case, this signed input here would probably come from my app. And when I do a transfer to you, it will generate an external input to my account on the blockchain that it should transfer a message or money to your account. Yeah. Okay, well, that's kind of the vision people have for using these smart contracts. programming, for example, financial services. Now, an obvious problem with this here is that if anyone can just give an input, and in particular, if anyone can have its smart contract just generating inputs for other smart contracts, it would be very easy to do a denial of service attack on a system like this. I could just make a smart contract that when it gets an input from me, then it will generate a million billion calls on other smart contracts. Now all these 1,000 servers in the world have to run all these million billion inputs, and I just took the system down. Okay, so to avoid this, there is this notion of energy, or gas as it's called sometimes, which basically just means that to execute one step on a smart contract, you need to pay for it. And basically what you could envision is that you're paying for at least kind of the energy it takes to run it, let's say the electricity that it takes for all these machines to run this call that you ask to have run. That's why it's sometimes called, like the unit in which you pay is called energy. Sometimes it's also called gas. You have to put some gas in the system to run it for fairness. So the way this would, one way this works, and the typical way it works, is that all the gas to pay for all the execution is paid by the account that does the initial call, the one that gets the external input. So when I make an input to my own account here and say, here's an input, I would like to trigger you and you should call some other contracts for me, please. You also send along some unit of energy and you pay for this. Often there is an exchange rate that's not one-to-one, but let's just imagine it's one-to-one now that we're paying gas in the cryptocurrency. So what will happen when I give this input is this gas here that will be sent along now, it's subtracted from my account. And again, I will now do a very simplified system where each call just costs one. But of course, if you do a call that takes a lot of executing, it will cost more than if it's a very simple call that only takes a little bit of executing. And that's a big nightmare in doing execution semantics for these smart contract languages, but it's not something we concern ourselves with in this course here. So let's make it very simple and say each call just costs one. Okay. So that's how it works. I make an external call to my own smart contract. Then when it makes a call to the next smart contracts, it sends along the remaining gas. So already this was a call. So I paid 2 and 1 was consumed for running this thing here. Then it made a call up here. Now, if that calls another thing up there, it will send along the remaining gas. But then here, I kind of screwed up. I sent along too little, so there's no more gas left. So probably an exception is called here, or maybe a complete rollback here. But again, this is complications that the poor people that have to make the programming languages for smart contracts and the semantic systems and the economic systems have to concern themselves with, not us. The purpose of this talk here is just to illustrate what are these cryptocurrencies and what are smart contracts. Okay? That's the idea of paying gas, is that you really pay for having it run, and therefore there is no way to do a denial of service attack on the system. In particular, this cryptocurrency that is being consumed here, that is being subtracted, you can think of that as being put onto some kind of system account from which then it's used to pay the servers running the system. And the way it's typically done in blockchains is, I mean, we have these servers, and in each kind of step, there is one server that makes the next block. And then you just take some of the money that came from the gas or energy, and you use that to pay the server that was kind enough to make the next block. So the cryptocurrency is paying for the totally other broadcast channel that's upholding the value of the cryptocurrency. So you get this closed system where the system is kind of paying itself for running. Okay. So there are no denial of service attacks, or contraire. If someone will make 1 million calls to the system now, it will be paying this gas every time, and all the servers will be like, thank you, because they were actually pouring money into the system. Okay, That's the notion of energy and gas. Then the system might look a little bit boring until now, because smart contracts can call themselves and based on external inputs. But that kind of comes short of doing what I said earlier, let's say to transfer money based on, let's say, the euro to US dollar price reaching a particular value on a particular day. So to make smart contracts able to react to events in the real world, there's this notion of oracles, which are importing kind of values from the real world onto the blockchain where they can be seen. So in the simplest form, it's just a smart contract that can react to external inputs, but the external inputs will be like the owner of the smart contracts are giving commands to the smart contract saying, publish this value, publish this value, publish this value. So the smart contract is publishing a sequence of values. And these we can think of as values that the account owner is reading off out in the real world. So it's sitting and constantly watching the US dollar to euro price, for example, and uploading them to the smart contract. Now, of course, this would allow, if we did it that naively, it would allow the owner of that smart contract to manipulate the system by giving a false price. So what you would typically do is, instead of having one smart contract, you would have, for example, let's say 3 independent companies or parties uploading the same values. And then you would just take the value, let's say, that's reported by 2 of them. And then already you would have protection against 1 corrupted oracle. You could also do 13 and then have security against 6, and so on. Well, I mean, that's something we saw before, right? You get robustness by replication and then taking majority. So the cool thing now is then you can use these oracles to import real values from the real world. And then suddenly we can do these smart contracts and have them actually trigger events based on things that happened in the real world. It could also be that there is a smart contract that is being run, say, by what in Denmark is called tinglysning, where they would upload everything that goes through them so it can be seen by these smart contracts. Or we could have some independent companies import them and then take majority of what they claim to be reading off. So you could have all kinds of values that is today kind of underlying how society is running appear on these chains and then do contracts based on them. I might, for example, put up a smart contract which would transfer you, I don't know how much your house is worth. So if you have one, let's say 2 million, if the oracle that's reporting tinglysning at some point during the next 3 days reports that you have transferred ownership of your house to me. That's what tinglysning is for in Denmark. It keeps track, for example, of who owns a house. Yeah. So today, if you want to transfer ownership of a house, that is terribly complicated. You escrow money in the bank, but we could also imagine a crazy future where I make a smart contract that says, I put 3 million into the smart contracts. They can't be made go out. The only thing this smart contract can do is, if it sees the oracle that is tinglysning, within the next 3 days, report that your house has been transferred to me, it will pay you the money. Otherwise, after 3 days, it will time out and transfer the money back to me. Then you could use that completely independent of any kind of lawyer or bank to transfer ownership of a house in response for money on a cryptocurrency. I'm not here advocating that is a good idea, but I'm saying this is kind of the vision that's being touted, and why studying smart contracts, how to implementing, how to do the smart the programming languages for smart contracts on top of them is kind of a searching research topic in academia. There is this very new future you could imagine where things work by decentralized smart contracts. Okay, that was a lot about oracles. Yeah, and this is probably the slide where I should have been saying it. But in particular, in this combination here of oracles and smart contracts, I mean, you could imagine a quite powerful future where even like micro contracts are kind of controlling how microscopic parts of our society and digital infrastructure is working. Yeah, there's a very, I think from a distributed systems point of view, there's at least one interesting aspect here of this vision, which is normally in the real world, I mean, there's not a single transaction going on in our economy, our societies, without some kind of contract underlying it, which is resolving what should happen if someone is not fulfilling their role. And what you then do is, if you pay money and you don't get your service, is you have to take them to court. And that means, and this is important that you can do that, because a contract is not worth anything if the peers involved in the contract cannot trust that the contract will be enforced. So what's really interesting about contracts and what makes them a contract is that they can be enforced and that you can trust that they're enforced. And that opens up a lot of transactions. You couldn't do it if you couldn't establish this trust with contracts. So a lot of the economic value we're generating in society comes from the ability, I mean, to make contracts that we know will be enforced. Now, the way we do it in society today is we do it in a centralized way. We say there is a judicial system. And if you don't fulfill the contract, I take you to court. But that's a very centralized way to do it. I mean, there's this one judicial system we should all trust, say the Danish one. And that might make it hard to make contracts across countries, in particular for all parties to believe that they will be faithfully upheld. And it also makes it extremely expensive to uphold them, because when you need to uphold them, if someone cheats, you have to take them to court, you have to use a lawyer, and they cost a lot of money. So you can't make contracts about like tiny transactions. However, I mean, smart contracts is the dual. I mean, with smart contracts, you can make a contract as easily as sending a package on the internet today. And you don't have to pay to uphold them, because they are automatically upheld, because they're a piece of code. And when the conditions for their execution are upheld on the blockchain, they will just be executed under the assumption that no one took over more than half of the machines in this huge distributed system. So you're establishing trust in a fundamentally new way. So you're saying, you know what, I trust the system because I trust that the ones that run the system don't trust each other enough that they will collude against me. So you're building trust out of a distributed distrust, so to say, instead of having a centralized component. And at least from a nerdy distributed system point of view, replicating something like a service or trust is interesting. And it's quite intriguing that you can establish trust out of distrust, at least. Okay. Yeah, and finally, maybe from a computer science nerdy point of view, it's also a nice story that maybe, there could be a future in which establishing good contracts and upholding them could be moved away from being a job that's upheld by lawyers, and instead making it a sub-branch of programming. You could imagine that over time, society could build up a huge public open source public database of standard contracts that can be reused and put together by programming, and then automatically upheld. That would certainly fundamentally change how we make contracts and how how they're executed. Finally, just a few words on how it is actually to program smart contracts. It's so far still a research area in progress. It's not so clear what these smart programming languages should look like, and particularly how to program them. And routinely, people write smart contracts which have them lose hundreds of millions of dollars because of bugs. That's the problem of having the code being the law. If you make a bug in something that can transfer your money away, it will just transfer all your money away, or have a hacker take all your money. And there is no way back, because that was the rule of the system, right? And the reason why it's hard to make these smart contracts or to program them securely is, if you look at what you have developed, if you have this replicated state machine with a lot of smart contracts inside it, it's actually a new virtual distributed system in itself, where each of these here is kind of the computational agent, and they can send signals to each other. And you could have this one call that one, call that one, and then call that one back again. And maybe this one was not in a good state to be called at this point, and so on and so on. So we actually kind of virtually back at the same system again. We started with 1 million servers. We did some nice distributed system stuff to make a nice, totally ordered broadcast where everything is nice and ordered. But then we use that to emulate a lot of small state machines living in the same space that can talk to each other. And there you have your distributed system back again. But it's more of the flavor of distributed programming, which is a different kind of course. So we'll not dive more into that here. In the next videos, we will then dive into the nerdy distributed systems details of how on earth do we implement a totally ordered broadcast channel running on 1 million servers across, distributed across a planet. That, on the other hand, is a topic of this course, and it's very fascinating. So we'll be using a few videos on that. Yeah. That was the last slide. Thank you for listening.